he has also some first experience in Memristors fabrication too, and he's going to tell us how.
Okay, thank you for the introduction. So my talk will be even more specific than Professor Reed's talk. I will talk about resistive switching probed by a metal-insulator semiconductor bipolar transistor. At the beginning of my talk, I will give some the motivation for our study, which is aimed at understanding the conduction mechanism in resistive switching materials. The background section was already covered by previous talks, so I'll skip it or make it very short. I will then present the new device, the metal-insulator semiconductor bipolar transistor. We are using this device to measure resistive switching materials. I will show the experimental results and discuss what we can learn from these results. And if I have time at the end, I will show some additional features of the MISBT structure. So the motivation, I think it's pretty clear today that resistive switching is one of the most promising memory technologies due to its excellent scalability, potentially low cost, low switching power, high speed, and high performance by means of endurance and retention time. But the implementation of this technology is still limited by the lack of understanding of the conduction mechanism and the switching mechanism. And I'm talking here about electron conduction, of course. So a very basic background. Again, this was already covered. But I'm talking about a very thin insulating film sandwiched between two electrodes. In most of the cases, these are metal electrodes, but it could be a semiconductor, like in my device. And you can see this table here from Wasser's paper that already Professor Kank showed this all kinds of effects that are responsible for resistive switching. In this talk, I will focus on the valence change memory effect. And I will talk about the bipolar behavior. Bipolar here means that the change from a high resistance state to a low resistance state, or the set process, occurs at the opposite polarity from the reset process, or change from a high resistance state to a low resistance state. So this is a theoretical IV characteristics of a bipolar resistive switching device. We have reversible switching between two different states at opposite polarities. And as was already mentioned here, in most of the cases, the switching is due to the formation and rupture of conductive filaments. So the conduction at the low resistive state is through these filaments. I will now show the new device structure, the metal-insulator semiconductor bipolar transistor. But before I show it, I will start with a familiar standard NPN bipolar transistor. We have N-type semiconductor layer, then a very thin P-type layer, which is the base. It should be thin relative to the diffusion length of minority carriers, and then an N-type emitter. So we have two junctions back to back in the forward active state of the device. The base emitter junction is forward biased, so electrons are injected from the emitter into the base. And the base collector junction is reverse biased, so electrons or minority carriers are collected here. And at the collector terminal, we're measuring the minority carrier, or electrons in this case. And at the base terminal, we have majority carriers, or holes in this case. Now, we place the N-type layer with a very thin insulating film. And this is the metal-insulator semiconductor bipolar transistor, or MISBT to be short. So we still have this base collector p-n junction, which separates the minority and majority carrier currents, or the holes and electrons. And the main difference is that the injection of electrons and holes from the emitter metal is through this very thin insulating film. by tunneling or any other conduction mechanism through this thin insulating film. In this study, we are using an indium phosphide substrate, and the PN junction is indium gallium arsenide. The reason is we originally designed this device for high-speed applications, but as soon as we started measuring these thin insulating films, we saw the resistive switching behavior, and that was very interesting. So we're our study is now focusing on the resistive switching. The switching materials in this study were silicon nitride deposited by plasma-enhanced CVD, aluminum oxide by atomic layer deposition, and hafnium oxide by atomic layer deposition. The thickness we tried various thicknesses between 5 to 10 nanometers. I will now explain the principle of operation of the MISPT using a schematic energy band diagram. So we are looking at a metal-insulator semiconductor with a PN junction structure. The p-type layer is highly doped, so we neglect any bending here, and for simplicity, we'll assume flat band conditions at equilibrium. And now we start to apply positive bias on the base terminal. So the metal Fermi level increases, and electrons are injected into the valence band of the base, which is, of course, the same thing as holes that are injected from the base to the metal, and we'll start measuring base current. Now we increase the voltage, and at some point we will have injection of electrons from the metal through this thin insulating film to the conduction band of the base, and electrons that are injected to the conduction band and do not recombine at the interface or inside the base layer will then be collected at the collector terminal, just like in a standard bipolar transistor. So to sum up this last slide, we can see the device structure here, and we have the base terminal. Out of the total emitter current here of the metal, we have the base terminal that measures hole current or majority carrier current, and collector terminal that measures the electron current or minority carrier current. So the advantage of this device over the standard metal-insulator metal or metal-insulator semiconductor structures that are used to measure resistive switching is that the standard devices are two-terminal structures, so they measure only the total current. In the metal-insulator semiconductor bipolar transistor, we have a three-terminal structure, so we can separate the minority from majority carrier current. And the most interesting thing to study the conduction mechanism is the ability to monitor the minority carrier current. This is the measurement setup. Our device is connected by a probe station to the semiconductor parameter analyzer. The base and collector terminals are connected to the adjustable voltage source. The emitter is connected to its ground. And we measure separately the base current and collector current, or the holes and electrons current. We're using here the internal current limit of the device to prevent damage or prevent hard breakdown of the device. This is the measure, the experimental results of our resistive switching device with a 5 nanometer hafnium oxide. The hafnium oxide showed the most impressive resistive switching. I'll start by showing only the majority carrier current, only the holes current, because this is similar to what you will see in a two-terminal structure. So we can see a very impressive change of the resistance, about 3 orders of magnitude. This is the set process change from high resistance state to a low resistance state, and we're using here the current limit. And at the opposite bias, you can see that this change is reversible. So at the opposite bias, we we will reset back from a low resistance state to a high resistance state. Now I add the extra information provided by the MISBT structure, which is the electron current or minority carrier current. I'll start just by noting that at negative bias, as you can see from the energy band diagram, we wouldn't expect any electron current, and as expected, there is no collector current here. And at the positive bias, you can see that the switching occurs simultaneously for both currents. And at the low resistance state, here we have very significant injection of minority carriers. And I will now, in the next few slides, discuss this low resistance state characteristics. I will divide it to 3 different voltage levels and start with a low bias. As you can see from the energy band diagram, in this case, just like the negative base bias, we do not expect any injection of electrons, and the collector current is negligible. But as we increase the bias into intermediate levels, we are measuring the collector current increases exponentially with a Boltzmann factor. The reason is, if we look at the energy band diagram, you can see that the metal Fermi level increases, and the injection of electrons into the conduction band becomes possible. It is consisted of 2 serial steps. The first step is thermal excitation from the metal Fermi level to an energy band aligned with the base conduction band, and then electrons cross at constant energy from this energy level into the conduction band. This constant energy thing is very important. I will mention it again later. But you can see from this dependence that the limiting step is the thermal excitation, and that's why we're getting a Boltzmann factor. I will discuss this Boltzmann factor again later because we can use it for additional features. When we reach high voltage levels, high here means that the metal Fermi level is already aligned with the base conduction band. There's no need for thermal excitation. So other processes limit the current, like the transmission coefficient through the insulator or the serial resistance of the base. I've shown only the hafnium oxide results because they are the most impressive, but we're getting the same behavior for the other insulating films we have tested, the silicon nitride and aluminum oxide, as you can see here. So it looks like a very general phenomenon. So what we can learn from these results, the most important thing for the conduction mechanism is that from the description I've just told you, it looks like the electrons cross the insulator at constant energy. And I'm saying here tunneling, but I'll discuss this tunneling later because this cannot be tunneling through the entire film. And the important thing is that any other mechanism which requires electron energy loss, like ohmic conduction, mode hopping, Poole-Frenkel, and other very popular conduction mechanisms, cannot account for these results. And we're getting the same behavior for all the tested materials, so it looks like a general mechanism. So again, I'm saying here tunneling, but it is clear that it cannot be tunneling between the electrodes or tunneling through the entire film because we're getting very high current densities, and tunneling through 5 or 10 nanometer films cannot provide such high current densities. But we remember that we are talking about resistive switching materials, so we have these conductive filaments. And the possible conduction mechanism that the filament is formed towards the base electrode, and it stops somewhere very close to the base electrode. And then the tunneling occurs from the edge of the tip into the base electrode. It should be something like 1 nanometer layer, so tunneling can provide such high current densities. And it is necessary, as you can see from the energy band diagram, that the entire voltage drop is across this tunneling gap. So this model was suggested by the HP group in 2009. We'll call it filament-assisted tunneling, and the tunneling is across this very thin tunneling gap. But one question that remains open in this model is what is this tunneling gap, or in other words, why would the filament go all the way towards the opposite electrode and not go all the way and connect to the electrode, like Professor Rees showed earlier? Why don't we get some kind of short circuit? What's the difference between this layer here and the bulk layer? So we are not sure. We have a few speculations. The first option is that this is some kind of residual of the bulk insulator, like the hafnium oxide. But then again, it's difficult to explain what is the difference between the hafnium oxide here and the hafnium oxide at the bulk. Other options are this is some kind of native oxide. In our case, the base electrode is a semiconductor, indium gallium arsenide. So this could be some kind of native oxide of the semiconductor that was formed, and of course it has different material properties than the insulating bulk. And any other interfacial layer, some kind of interface between this bottom electrode and the insulating film, or between the bottom electrode and the conductive filament itself, because an interfacial layer can be like about 1 nanometer, and of course has different material properties than the bulk. So I've discussed our experimental results with the conduction mechanism. Now I will show you two additional features. One which we have just very recently started to work, and the other is an experiment we plan to do in the future. So the first thing is temperature extraction. The filament temperature is very high because the filament is very thin, and high current density flows through this filament, and it heats up to very high level temperatures. Many papers are trying to model it, and it's very difficult to measure it. And this issue is very important for reliability issues and also for the switching mechanism, because the switching is enhanced by temperature. In our device, due to this Boltzmann factor dependence, under these bias conditions, we can see that the current is limited by the thermal excitation. So we can extract from the exponential slope of the IV characteristics, according to Boltzmann factor, under certain assumptions, we can extract the temperature, and you can see here the temperature extraction from these parts of the IV characteristics. Another feature is we have seen very significant injection of minority carriers. So if we'll take this metal-insulator semiconductor structure and use a direct bandgap material, we'll have injection of minority carriers only where we have a filament that was formed that injects these minority carriers. So if these minority carriers will be injected into the semiconductor, and somewhere they will recombine and radiative recombination. So we can take an image of the light emission and make a mapping of the filaments, so we can tell whether we have a single filament or multiple filaments. We can tell their position, their density, at least with a resolution of the diffusion length of the minority carriers. So to conclude this talk, I've shown a new device structure, the Metal-Insulator Semiconductor Bipolar Transistor, which separates minority and majority carrier currents. We have tested 3 different resistive switching materials, and all materials shown a very significant injection of minority carriers. So our experimental results support the filament-assisted tunneling model. Thank you for listening.
Thank you. Question? Yes, Jakob?
You probably have a large resistor in the base to control the cell procedure. In this case, where the switching takes place, the voltage drop on your dielectric will change. And you show all the time the same inclination of the band at the band diagram. Do you control the changes in the voltage drop of the voltage drop in the two dielectric layer? This is the question.
Okay, so the question was about the voltage drop across the base layer.
Yes, dependent upon the set reset state.
Yeah, we do not control the voltage drop, but you can see that first this is a very highly doped layer, so the resistance is not that large. Okay, although it is a thin film, we have the base is very highly doped, and you can see here we didn't do much extraction, but probably in this voltage area we can extract the base resistance and tell the extra voltage drop after this voltage drop, like about 1 volt on the insulating film. When we increase the bias from here, the extra voltage drop could be on the base layer, because this is the limiting process here. Yes, well, it's a good question. The question was about transient measurements. We still didn't do transient measurements or measurements at other frequencies, at higher frequencies, where we plan to do it in the future. It's a good question. Thank you.
Okay, we are slightly behind in time, so thank you very much again.